Hello. All right. So we're moving on to chapter 4.2. And this is going to be over a new type of function, exponential functions. So exponential functions. Functions of the form f of x equals c times a to the x. So these are new. These are definitely not polynomials. Okay, so it's a different type of equation. So everything that we've done up till now has been a polynomial. Lines have been polynomials, horizontal lines have been polynomials, quadratics, cubes have been polynomials. And so now we're dealing with our first non-polynomial function. What makes them different is for a polynomial, polynomials are of the form x to the n, where this number is just a real number, any number. Any number on the number line. Where this number is a integer. Okay, so examples of this would be, again, we did polynomials in the last exam, but 5x squared, or maybe 3x, or 7x to the 10, things like that. Okay, now exponentials, on the other hand, okay, these are different. These are times to the x. So notice the position of where the x is, the exponent. That's pretty much why it's called an exponential. Sorry about that. So exponential because the x is in the exponent. Now this guy up here, this again can be any number on the number line. Any number on number line. Whereas this number is special. This number, the number that's attached to the x. So here this is like an expression that's pieced together. And so this is what we call the base. And we're going to talk about what the base can't be. It turns out that it must be positive, and it can't be 0 or 1. So it must be positive, and it can't be 0, can't be 1. Right? But anyway, so that's the difference between a polynomial and an exponential. So polynomials have the x as 5x squared, 3x, 7x to the 10. Exponentials instead are things like 3 times 5 to the x, or making something up, pi times 1/2 to the x, 8 times 4 to the x. Okay, they're completely different types of functions. And so I want to go in Desmos and show you that they're completely different functions. So for polynomials, we have, for instance, x squared. Okay, so there's x squared, whereas 2 to the x is the exponential. And notice that they're completely different. Okay, the exponential starts out pretty flat, and then it goes upward, and it actually is steeper than the x squared. Notice it starts to almost look pretty flat. Let me change the y-axis so you can get a better idea. So if I change this from, let's say, negative 10 to 1,000, okay? So the parabola kind of goes up slowly. The exponential increases extremely rapidly. All right, we're going to go more into the graph in a bit. But for now, just some stuff about it. So again, A is called the base. Okay, a is the number here. And so, again, we call that the base. Okay, it has to be greater than 0, so it can't be 0, but also it can't be 1, just like I mentioned over here. So it must be positive, can't be 0, can't be 1. C can be any number, but C can't be 0. And the only reason C can't be 0 is if C was 0, you would have, let's say, 0 times 3 to the x, but that's just 0. So that's pretty boring. So for now, C can't be 0 because the graph would be boring. Anyway, so just like we're dealing with problems here, let's say when you're dealing with a polynomial, I'm going to go back to polynomials. All right, so for instance, you had ax to the n plus blah, 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 plus, this is a to the n, plus a1x plus a0. Now the number at the end, that was the y-intercept for all polynomials. If you had just a number like mx plus b, that was the y-intercept. But remember that we're dealing with exponentials, that exponentials are completely different. Exponentials are of the form c times a to the x, and for exponentials, the c in the front is the y-intercept. All right, my cats are going crazy. All right, so again, when you're dealing with an exponential, for instance, I'll just go to Desmos. If I have 3 times 2 to the x, notice that this number up front would be the y-intercept, which is 3. Notice that's the y-intercept. Let me go back to a normal graph. Okay, if I change this to 5, the y-intercept changes to 5. If I change this to a 1/2, y-intercept changes to 1/2. So whatever the number is in front is the y-intercept. Anyway, so our first thing we're going to do is we're going to look at some graphs, or some tables, sorry, and we're going to create the exponential equation that makes them. All right. So what we're trying to do is we're trying to create the equation y is equal to c times a to the x. So we already found that c is the y-intercept, like I just mentioned. It turns out this base can be found too. This base is what we call the multiplier. Let me get all my colors lined up. So this a, I didn't have room up there to write it, but this a is a multiplier. What you do is you look at your y values and you see what they're multiplying by. Whatever it is they're multiplying by, that's going to be your a. So if I look at this first equation, I can see that here's my y-intercept. Let me try to color code it. I'll do red for the y-intercept. X is 0, so that's the definition of the y-intercept. The y value when x is 0. And if I look at multipliers, every time I go across from one y value to the other, I'm multiplying by 2 times 2 times 2 times 2 times 2 times 2 times 2. And so here the multiplier is 2, so that means that a is equal to 2. Now that I have all that information, I can just plug it into my equation. And so the equation is c times a to the x. So this equation would be 1 times 2 to the x. Now 1 times anything is itself, so this is just 2 to the x. And that's it. That's my equation. So given a list of x and y values, I'm able to create my exponential function. And again, we can show that this is correct in Desmos. Here's 2 to the x. Let me put the 1 in front of it. And in Desmos, you can actually create tables. So I'm going to call this f of x equals. And then I can say this is f of x. And then I can say this is x. And so here we have 1, or 0, 1, 2, 3, 4. And so notice these numbers here, this table, lines up with the values that we have over here. Anyway, so let's go to the next one. The next one, we have our y-intercept is here. And my multiplier is a little trickier, but if I look through them, the first two, it's kind of hard to see. But notice that the multiplier is times 2, times 2, times 2, times 2. So my a is 2 once again. And again, 3/4 times 2 is 3/2. 3/2 times 2 is 3. So everything checks out. And so for my equation, it's y equals c times a to the x. So y equals 3/4 times 2 to the x. Okay? These two things here are completely separate and they do not mingle. You cannot combine. Do not try to simplify that because you can't. It's 3/4 times 2 to the x. The reason is that the 2 is raised to the x, but the 3/4 isn't raised to the x. In order to combine like terms, they both have to be raised to the same power. And since they're not, we can't combine them. So it's just 3/4 times 2 to the x. Here, I try to be a little tricky. I put the y-intercept here instead. And it seems a little weird with all the fractions, but if you ever encounter fractions like this and you're trying to find your multiplier, just do the numerator and the denominator separately. Here, notice that this is times 2, times 2, times 2, whereas on the top, it's times 3, times 3, times 3. So here, my a is 3 on the top, 2 on the bottom, or 3/2. And so my equation would be 1/4 times 3/2 to the x. Now, if I leave it like this, let me turn my phone on silent. Sorry about that. So 1/4 times 3/2 to the x. It turns out, though, that this is incorrect. And the reason is parentheses are everything. It's not just 3 to the x, it's the entire 3/2 to the x. So to fix it, you have to do 1/4, and then the 3/2 needs to be in parentheses. 3/2 to the x. If you forget your parentheses, it's incorrect. So you got to watch out. All right, so then this would be the correct answer. All right, next one. Again, we see the y-intercept is 0, 6. And here, what's it doing as we go across here? I'll start with the fractions. So notice that the bottom is going times 3, times 3, times 3. And what's the top multiplying by? The top is just not changing. When it doesn't change, that's just times 1. And so notice here, my a would be 1/3. Okay? So multiplying by 1/3 is the same as dividing by 3. So that's why we go to 18 times 1/3 is 6. 6 times 1/3 is 2. 2 times 1/3 is 2/3, and then it starts to get to the ugly fractions. But anyway, following my cue from the last time, it's y equals 6, and then I need to put the 1/3 in parentheses for it to count. Again, you cannot combine these. You can't say 6 divided by 3 is 2 because that is all sorts of incorrect and it makes Gilbert sad. You have to leave it like this. 6 times 1/3 to the x. Right? And now let's look at this last one. I just put this one there to show you stuff. So here we have 0, -2, but notice that there isn't a multiplier. We go from -2 to 5. We go to 5 to 12, from 12 to 19. So notice that this is different. Instead, this is +7 every time. So we're adding to get to term. Okay, whenever you add to get to each new value, this means it's not exponential, but instead it's linear. And linear is just regular y equals mx plus b, where b is my y-intercept, and the slope, adding 7, adding 7, adding 7, that's just the slope. And so my equation is just y equals 7x minus 2. Right? Anyway, so I just wanted to do that bottom one to show you that not everything's exponential and not everything's linear. But it turns out that these are really two very popular things, and I could go completely nerd out on the difference between the two. Just a little taste is usually things we produce, production is linear, because no matter how fast you can make something, you can only make a certain amount per time increment. So +7, +7, +7, +7, +7. If you're making toothpicks, +1,000, +1,000, +1,000. So anything you produce is linear, whereas population growth tends to be exponential. So population growth, there's 2 bunnies, and then there's 4 bunnies, and then there's 8 bunnies, and then there's 16 bunnies, and then there's 32 bunnies. So population growth, exponential, but production is linear. And there is a whole story about how those two interplay. But anyway, moving on to the next page. Whatever, Gilbert. All right, so properties about the graph of the exponential functions. So whenever you're dealing with an exponential, there's 2 ways the graph can look like. And again, I'll go to Desmos and I'll show you. So here's one version of the graph. Let me just put A. And let me go from 0 to 2. So there's 2 ways this graph can look. It can look like this, or it can look like this. It can look like this, or like this, like this, or like this, like this, or like this. And so we got to know the differences between the two. Notice that it changes shape at 1. To the left of 1, it looks like this, basically going downward. To the right of 1, it looks like this. And that's basically the main idea between the 2 shapes. So going back to our handout, first, this is a increasing one-to-one function. Oh, sorry. We're going to start with a being greater than 1. So on Desmos, we're only looking for values greater than 1. So it can be really small, really close to 1. It can be farther away from 1. But that's the only values we're looking at. So if the base Remember, we call a the base. If the base is greater than 1, this is what's called an increasing one-to-one function. The graph is smooth and continuous. We learned about it last time. Continuous means that you can trace without picking up your pencil. My domain, the domain is everything. But notice the range is 0 to infinity, but it never actually touches 0. Okay? Now this has to be memorized. Not necessarily for this section, but when we get into 4.4, you're going to have it memorized. So this problem, get my pen, give out, nope. Hold on, let me pause it, figure out what's wrong with my computer. All right, that was really weird. But anyway, so you have to have this memorized. That if you ever see an exponential, automatically you know what the domain is, and automatically you know what the range is. And this is, again, before we move it. You can get the graph, you can move it up, down, left, right. But before you do any up, down, left, right stuff, the range is 0 to infinity. Now, since it never touches the x-axis, meaning that this is a horizontal asymptote, okay, my x-intercepts are none, because it never touches. And the y-intercept, now in this picture it's 1, because notice there's nothing in front of it. So the y-intercept is, by default, 1. But in general, it's whatever the value of c is. Remember, before we had c times a to the x? It's whatever the number in front is. But I'm just, so I don't throw y'all off, I'm going by my picture here. The picture here has 0, 1, so I'm going to stick to 0, 1. Because the value of c that we're looking at in this particular example is 1. Asymptotes, there's a horizontal asymptote at y equals 0. Okay. And my key points are 0, it's 1, or in this case c. At 1, it's the a. And here this is 1 over a. Now if you were looking at it, if you were looking at c times a to the x, then this would be c times a, this would be c over a. Anyway, I don't really care too much about this, but that table is just some key points. If you really want to graph it, what you can always graph is the y-intercept. You pick a point to the right, you pick a point to the left, and then you create your sketch. Now, one thing I want you to notice, though, is what happens as the base gets bigger. It increases more rapidly. As the base increases. All right. So now let's look at the other graph. The other graph is the same picture, but if a is between 0 and 1. So now I'm looking at this side. And notice on this side, the graph flips across the axis. And let's talk about it. So if a is between 0 and 1, and again, examples of this would be 1/2 to the x, or maybe 3/4 to the x, or even 1/10 to the x. or even 0.3487 to the x. Anything where the base is between 0 and 1, we have a decreasing one-to-one function. The graph is still smooth and continuous. The domain is still negative infinity to infinity. The range is still 0 to infinity. The x-intercept still none. So notice a lot of the information is the same from above. The y-intercept is still going to be 0, 1. Did I put 0, 1 or 1, 0? Yeah, I put 0, 1. Asymptote is still the same asymptote, which is y equals 0. All that changes is now the points. Instead of it being 1 over a over here and a over here, the a is on this side, and the 1 over a is on this side. Okay? And so what happens here is, as the base gets closer to 0, it gets steeper. So notice that 1/2, 1/3 is smaller than 1/2, so it's steeper. 1/10 is smaller than 1/3, so it's steeper. 1/100th would be even steeper. 1 over 1,000th would be even steeper. So the closer and closer and closer it gets to 0, the steeper it's going to get. And again, I can show you on Desmos with my graph. Let me put 0, let me make this 1 right here. So notice that the closer I get to 0, the steeper and steeper and steeper. It can't actually equal 0. Notice the graph disappears. There's something wrong. And we're going to learn about why that is when we get to 4.3. But for now, just know that as you get closer to 0, the graph gets steeper. As you get closer to 1, the graph flattens out. All right. So let's do some graphing examples. The homework here is going to have you do some graphing. And what they're going to want you to do is they're going to get exponentials and they're going to move them up, down, left, and right. But before we do that, let's just find a couple of these points. So let's start here. Let's say we're dealing with 3 to the x. Let's go ahead and fill in the table with 0 in the middle. And remember, this is 3 to the x. So for y, it's going to be 3 to the negative 3, 3 to the negative 2, 3 to the negative 1, 3 to the 0, 3 to the 1, 3 squared, 3 cubed. And all I got to do is plug in what they are. You can use your calculator if you want, but this is fairly easy. I'll start at 0. Anything to the 0 is 1. 3 to the 1 is 3. 3 squared is 9. 3 cubed is 27. Okay, I go the other way. 3 to the negative 1. Now again, you can use your calculator. You don't have to though. 3 to the negative 1 is the same as 1 over 3 to the 1. The negative exponent just means that it's in the denominator. So whenever you see a negative exponent, it just really means that the expression is really in the denominator. Okay, so 3 to the negative 1 is actually 1/3. 3 to the negative 2, well, 3 squared is 9, but it just means that the 9 is really in the denominator, 1/9. This is 1 over 27. Okay, so let's go ahead and plot that and see what we get. So here's 0. Let's say this is 1, 2, 3, negative 1, negative 2, negative 3. So Let's start it at 0 again. So if it's at 0, the answer is 1. That's going to be right there. We're going to be guessing a lot of the time because it's really hard to get the exact value on a scale this big. At 1, we're going to pick 3. It's a little closer to the 5. Kind of right, a little above, right in the middle. At 2, it's 9. At 3, it jumps up to 27. So here, 27, about right there. And if I know I didn't give enough space, but if you wanted to add 4, the next one would be 81 because it's 3 to the 4th. And so the next point would be, let me add it in. So 4 would be all the way up here at 81. Okay, -1. And then after that, notice at -1, it's 1/3. And there's no way that you can, on this scale, especially this big, there's no way that you can tell the difference between 1/3, 1/9, and 1/27. So I'm just going to pretty much put them right on the axis. Even though I know in my heart they're not really touching the axis, it's just that they're really close to it. 1/27 is really close to the axis. 1/9 is really close to the axis. So I connect my dots. Let's start by drawing the horizontal asymptote at 0. Again, it's going to pretty much look like it goes through all those points. Just know that it doesn't. It's just you need a microscope to see it not touch. But anyway, I'm going to actually start showing it leaving around here. And there we go. Again, for the really small numbers, don't bother trying to separate it from the axis. It's so close you can't tell. All right. So here is 3 to the x. Now let's go ahead and graph the other one on the same axis. This next one is 1/3 to the x. I'm going to do the exact same thing. I'm going to do -3, -2, -1, 0, 2, 3. Going to go ahead and add a 4 there. And now it's 1/3 to the x. So here this is 1/3 to the 0, which is 1. This is 1/3 to the 1, which is just a third. This is a third squared, so that's 1/9. A third cubed, 1/27. This next one's going to be 1/81. So look at the answers from before and what they are now. These started small, 1/27, 1/9, 1/3. And notice that these are going in the opposite order. So if I do 1/3 to the -1, let me write it up here. 1/3 to the -1 is equal to 1/1/3. But you can fix it. I can say times 3/3. Those cancel. And you end up with 3. For the same reason, 1/3 to the -2 will be 9. 1/3 to the -3 would be 27. And if you wanted to, you could use your calculator. But you have to put the 1/3 in parentheses. 1/3 raised to the parentheses -3, for instance, 27. And so notice that this graph is going to look a little different. Let me make it in red. -3, 27. It's kind of like a flipped image. At -1, we got 3. That's the same value. And then from there, you can't really tell, and it just goes there. At -4, it would be all the way up here at 81. And so this graph looks like this. All right, and this is 1/3 to the x. There we go. So what do you notice about the two graphs? We notice that 1/3, 3 to the x, and 1/3 to the x are reflections about the y-axis. Okay? But if we remember from way back when this is actually exam 1 stuff, but if you remember from exam 1, we also learned that replacing x with negative x not replacing x with negative x. My brain just isn't working right now. When we were doing transformations, way back in exam 1, we learned that f of negative x was a flip across the y-axis, was a horizontal flip. Okay, so a flip across the y-axis is a horizontal flip. So they're the same thing. And so I want to show you that these two things are the same. It turns out that if I get 3 to the x, sorry, we'll look at it this way. If I get 1/3 to the x, I can write 1/3 as 3 to the negative 1. And negative 1 times x is 3 to the negative x. So this is why they're reflections about each other. It's that this equation is really exactly the same as 3 to the negative x. So you have 3 to the x, 3 to the negative x, and that's why they're reflections about the y-axis. Anyway, yeah. So 5 to the x, 1/5 to the x are reflections. 10 to the x, 1/10 to the x are reflections, and so on. Okay, so if I do a to the x, and let me make this from 1 to 2, and let me do g of x is equal to 1 over a to the x. So notice that they're always going to be reflections about each other, about the y-axis. Yay! Anyway, more fun stuff. Next, Euler's number. This section gets pretty long, but I apologize. So Euler's number. You know what? For this video, I'm going to go ahead and break it into 2 pieces. Let me see here. Should I? Make a graph. I'll just keep carrying through. All right. So Euler's number. So for Euler, notice his name. Euler is a very popular guy in math, and you have to pronounce his name correctly. So you pronounce it like Euler, O-I-L-E-R, but it's spelled, differently. And what this is this is a pattern that we use a lot. It turns out E, which you'll use a lot in calculus, Cal 2, and pretty much any math class after this, has a very fancy name. It's the limit as n goes to infinity of this pattern. And so here, this is the pattern. And so as n gets bigger, what is that pattern getting close to? It turns out that number is this. And it's just like pi, it goes on forever. And so we just call it e. So e. And as it turns out, e is by far the most popular exponential function. Again, I'll kind of explain why, but really you'll learn in calculus why it's the most important one. The reason why is that for e to the x, the y value at any x value is equal to its steepness. And that's something that's only true for this equation. So if the y value is 1, the steepness or the slope. When I say steepness, I mean slope. If the y value is 1, the slope is 1. If the y value is 2, the slope is 2. If the y value is 10, the slope is 10. And that's only true for this equation. And math people like that property a lot. Anyway, how do we get e on our calculator? There's two ways to get e. So if you want to have it raised to a power already, you press second, and then the ln button, which is to the left of 4. And notice that that has it raised to an exponent for you. Now, if you just want the e by itself, no exponent, then you can press second and then the division symbol. And then that brings up the e by itself. It's up to you. Usually you're going to be pressing second ln, because usually when you see e, it's raised to something. Okay, so now just for fun, let's go ahead and fill in this table. I'm going to round to, let's say, 3 decimal places. So plugging numbers in, I have second natural log to bring it up to the -3. I'll do 0.04, let's do 4 decimal places, 0.498. And then same thing, second e -2 now, 0.1353. E to the -1, 0.3678. E, anything to the 0 is 1. E to the 1, well, that's just e, but if you want to go ahead and write it out, 2.7183. E squared, 7.3891, and then e cubed, 20.085655. All right. Anyway, I just wanted to fill in a couple of tables of values for e. All right. They don't go much into it more than that, but yeah, e is pretty cool. We like it. But in the future, they're gonna start showing e in your problems, and they don't want you to freak out. Remember, e is just a number, just like pi. It's a number that goes on forever. But yeah, 2.71828. So these next examples, I won't do all 3 of them. I'm just going to do maybe 2 of them. I'll save the other one for you to do as an extra video. But what they're going to want you to do is get graphs like we did here, or like we did at the top of this page, And they're going to want you to basically do some really basic transformations. They don't get too crazy with it in this section. What they're going to want you to do is they're going to want you to make the graph go left or right. So before we start, when you're dealing with a function, okay, we have the exponent is the inside. When we did transformations back in exam 1, remember there was stuff that affects the inside and stuff that affects the outside. So for exponentials, anything in the exponent is the inside, whereas, and let me move this further here, where everything out here is the outside. Okay, remember inside is x values change, whereas the outside, the y values change. So they just want to do some really basic stuff with exponentials. So notice in this first part, this is on the inside. So in this one, the transformation makes the graph go, and inside's the opposite of what it looks like, so it makes the graph go left h units. Left meaning it goes this way, if h is positive, or right h units if h is negative. Remember, it messes with your brain. Okay, so left h units if it's positive, it goes right if h is negative. Now, if you see the plus or minus k, I got all my colors all mixed up. I use green for the inside, so let me stick with that. And I use yellow for the outside. So this stuff's on the outside. And so this is going to do exactly what we think it's going to do. This transformation makes the graphs go up k units if k is positive, or down k units if k is negative. Anything on the outside does exactly what you think it's going to do. Nothing changes. Okay, now we have the negative sign. This is the flipping. This negative sign is on the outside. So it's going to affect the y values. This flips the graph along the... Now, you may say that, but Gilbert, you said that outside stuff is y values, so why are you going to write the word x-axis here? Well, the reason is the x-axis is really y equals 0. That's why. There's the y. So if the negative's on the outside, it flips across the x-axis. Basically, it changes all the signs of all the y values. If the negative is up here, notice that this is on the inside, and this transformation flips the graph along the y-axis, or we can think of it as x equals 0, and this changes the sign of all the x values. All right, so let's do 2 of these, and then I'll save the other one for you to do on your own. So the first graph says graph f of x equals 2 raised to the x minus 3 minus 5, and be sure to also graph the asymptote. All right. So the first thing we're going to do is we have to graph what's called the parent function. Because I've got to know what the x and y values are doing before I change them. I got to know what they are first. So Before I do anything, I notice that my base is 2. So my parent function is just 2 to the x. So I'm going to go ahead and just plot some points. Right? And if I need to do more points because of the shifting, then I'll add more points as needed. So negative 3, well, let's start at 0. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. 2 to the negative 1 is 1/2. 1/4. 1/8. Okay. And now what we're going to do here is look at what's being done. We got some very basic transformations going on here. This one is telling me right 3 and then down 5. So I'm going to go right 3 and then down 5. Okay. So here's my values. Negative 3, if I go right 3, that gives me 0. Negative 2, right 3 is 1. Negative 1, right 3 is 2. 3, 4, 5, and then finally 3, right 3 is 6. And then down 5. And here you can use your calculator if you want, because fractions get a little nasty. And you can use the decimals. 1/8 down 5, negative 4.875. 1/4 down 5, negative 4.75. 1/2 minus 5, negative 4.5. 3 minus 5, sorry, not 3. 1 minus 5, well, that one's easy, but just for the sake of typing it in, negative 4. Okay, then we have 2 minus 5 is negative 3. And then you have 4 minus 5 is negative 1. And then finally, 8 minus 5 is 3. All right. Now, as far as horizontal asymptotes go, the original one, by default, the horizontal asymptote is y equals 0. But since I'm going down 5, my horizontal asymptote here is y equals negative 5, because we went down 5. So let's try to graph it. And the values are kind of close to each other, so I'll do my best. But if each tick mark is 5, that means that the horizontal asymptote is here at negative 5. And then I have 6, 3, really tiny. 6, 3. Ugh, brain fart. 5, negative 1. 4, negative 3. And notice we're already pretty much at the axis. 3, negative 4. And then from there, you can't really tell. It's pretty much right on the axis from there on out. So looking at the graph, you can see that it's going to straddle. It's going to get so close to y equals negative 5, you can't tell the difference. Up until about 2. And then it's going to start going up. Now I need some more points to help me out. So I'm going to add some points. Let's say we have 4, 16, and 5, 32. So here, if I go right 3, this is 4 plus 3 is 7, 5 plus 3 is 8, and then down 5, 16 minus 5 is 11, 32 minus 5 is 27. So 7, 11 will be a new point. Man. And 8, 27 will be another point. and then from there. All right, but anyway, there's my graph. Now on your homework, it's just going to say pick the right graph, and it's going to show you 4 pictures, but that's how you would do it. They want you to do it with transformations. They don't want you just to plug every x value in and sketch points that way. They want you to plug all the x values into the original and then transform them to get the new x and y values. All right. So this one's exactly the same as the one above, except it's with 1/3. Instead of a 2 to the x, it's 1/3 to the x. So I'm going to skip that one. I want to go to the e, just because it seems scary because it's e. All right. Let's see if I can cheat here. Can he do it? Can he literally just copy and paste these values because he doesn't want to write them all over again? Copy, Control C. No. I guess not. Duplicate. I'm just being lazy, guys. I don't want to write all that stuff over again. Lazy Gilbert. Lazy Gilbert. Lazy Gilbert. There we go. All right. So I have my values for e to the x, and I want to do stuff to them. So if I look at my graph, notice there's the inside and the outside. And so what this is saying is you're going to flip all the x values. Okay, whereas this one is just saying down 10. So here I have down 10. And for this one, I'm going to flip. All right. And for the sake of just having some more values here, let's say this is 4. And what's e to the 4? 54.5982. All right, so if I flip all these values, this becomes 3, 2, 1, 0, -1. Excuse me, -2, -3, -4. Now down 10. So 0.0. I'm just going to use 2 decimal places. -10, -9.95. These are just approximations. 0.14 -10, -9.86, 0.37 -10, -9.63, 1 -10, -9, then e -10 are 2.72 -10, -7.28, 7.39 -10, -2.61, 20.09 -10, 10.09, 54.59, or 54.60 -10, 44.6. So I have everything I need, and now I just got to plot all these points. Now here, the horizontal asymptote, again, by default, my horizontal asymptote is y equals 0. But since I went down 10, my horizontal asymptote is y equals -10. So at -10, have my horizontal asymptote. And let's see if we can plot our graph. And 3, about -10. And everything from 3 onward pretty much is going to look like it's right on the line. 2, -9.86. 1, -9.63. -9. Still hard to tell. -7.28. So now we start getting somewhere. Starts to go up a bit. -2, -2.61. -3 hops up to about 10. -4 hops up to about 44.6. Right? And if you wanted to add in more, you could. For instance, 5. I think e to the 5 is going to be off the grid. Yeah, 148 point. So the next one would be 10 less than that. So it would be, yeah, off the grid. So anyway, there we go. Now all I care about really in this section is that you're able to identify the transformations. Know if it goes up, down, left, right, by how much, and then tell me what the new horizontal asymptote is. And that's just found by the y transformations. How far up or down did it go? Right? So try the one at the top of the page on your own. But we're going to do some word problems and then we're done. So this section finishes off with some word problems. And you may remember this formula from way back when you were doing in college algebra from high school. But we have something called compound interest. Now what compound interest is, and if any of you are paying loans or stuff, you're very familiar with compound interest. We have, I'm going to say, let's say this is January. And let's say we have December. And let's say you buy a car and I really don't know what the interest rates are for cars. But anyway, let's say they tell you that the APR is 12% interest per year. That means that whatever you borrow, at the end of the year, you're going to be paying 12% more, 12% of whatever you borrowed in interest per year. So if you borrowed $100, at the end of the year, you're going to be paying back $112. So let's say in January you borrow 100. So in December, or well, next January, you'd have to pay back 112 because the APR. But what compound interest does is it splits that up. I'm just going to put 6. So what they do here is the APR said it was 12% per year. So they're still going to say that that's true, but they're going to split it as 6% and 6%, because 6 plus 6 is 12. And so in the first 6 months, you're going to pay 6%, and in the second 6 months, you're going to pay 6%. So in this case, if you borrow $100, after month 6, I'm counting on my fingers, guys, because I'm really bad at this. January, February, March, April, May, June. And June, they're going to want 106 back. But then in December, they're going to want 6% of the 106. So 106 times 1.06, and that's $112.36. So notice that if they break it up into 2 pieces, you end up paying a little more back instead of the full amount. I mean, instead of 112, you're paying back a little extra. So that's the idea, and they can keep on doing that. You can split it up into 4 sections instead. And in that case, it would be 3% every time, because 4 threes gives you 12. And if you do that, you would have 100, then you'd have 103. So 100 times 1.03 is 103 times 1.03 again, 6 months in, times 1.03 again, 9 months in, times 1.03 again, and then in December, you'd be paying 112 and 55. And yeah, so the more they break it up, you pay a little bit more per year. So notice APR is a very misleading term. They say 12% per year, but if they break it up into a bunch of pieces, it's actually a little higher. It's not just 12%. In the second example, notice it's 12.36%. In the example below that, 12.55%. Anyway, that's just me nerding out over this. But really, Gilbert, I don't care. All I care about is the math. Okay, well, we're going to deal with this formula. And in this formula, we have accumulated value. It's just a really fancy word for the final answer. We have the principal. This is the really fancy word for the initial amount. We have the rate as a decimal. That's the APR. We have the time in years. How long are you taking your loan out? And the number of times the investment is compounded per year. Now, this last part tends to be a little confusing for people, so I wanted to break it down. Okay. So if something is compounded annually, annually means that you only have to pay them back once a year. And so that would be n would be 1. Semi-annually, pay back twice a year. That's 2. Quarterly, 4 times a year. So that's 4. Monthly, 12. Daily, 365. Unless they tell you something else. Sometimes they'll say use 360. If they tell you to use a number, use it. But usually if they don't say anything, daily is 365. And then continuously is infinity. And we'll go into that later. All right. So anyway, let's do word problems. Ready? If I confused you with my little attempt to do that, kind of ignore. Be like, whatever, Gilbert. And just focus on this formula. All we're going to do is we're going to plug into it different values. So suppose you have 500 bucks. So 500 is invested. Invested is the starting amount. So that has to be my P. Pays 6% per year. That's going to be my R. But again, you have to write it as a decimal. Under the following compound options. And notice that it's going to be after 10 years. So T is equal to 10. So for my formula, I already have a lot of information filled in. I know that P is going to be 500. I know R is going to be 0.065. N, I don't know that yet. N, I don't know that yet. But this is going to be 10. And so all I'm doing from equation to equation is just changing what the value of N is. Changing these two numbers. So annually means that N is equal to 1. So my formula is A equals 500, 1 plus 0.065 over n to the n times 10. And the value here is just 1. And so this is the straightforward idea here. If I type all this in, 500, 1 plus 0.065 raised to the, and then you have to open up a parentheses, 1 times 10. I have 938 and 57 cents. Okay, money stops in pennies, 2 decimal places. Why? Because they're pennies. Whenever you're dealing with money problems, it's always going to be 2 decimal places when you give your answer. I've seen weird things. All right, and notice this. So if you only have to, if your money only gets updated once a year, then you get the full 6.5%, and so $500 turns into 938.57, and this is once a year for 10 years. So $500 after 10 years will become $938. Now here this is n is equal to 4. So I have 500, 1 plus 0.065, and I'm changing this to a 4. So I go ahead and I can recall the last thing I typed in by pressing second enter. And I'll just type it in again. 500 parentheses 1 plus 0.065 divided by 4 raised to the parentheses 4 times 10. And notice that gives me 952.77. So if you have your money updated every season, 4 seasons per year, then instead of getting $938 after 10 years, you'll get $952. And notice that's pretty good. You can subtract the two, 952.78 minus 938.57. That's about, that's plus $14. That's kind of good. Not really after 10 years, that's kind of nothing, but now if it was monthly, I have A is equal to 500, 1 plus 0.065, and now all that changes is the number on the bottom becomes a 12. So 500, and you think, oh, if you instead of doing it once a year, if you do it 12 times a year, oh, you should get a lot more money. It turns out you don't. 0.065 divided by 12 raised to the 120. I'm just going to type in 120. 12 times 10 is 120. So you get 956 and 9 cents. And so doing it 4 times more as often, we get 956.09 minus 952.78, 331. Finally, if it was daily, what if you updated your account every single day? You think you would get a lot more, but again, just like before, it turns out that you don't get that much more. The main point here is noticing how I'm using the equation. I'm trying to show you that n appears twice in this equation. So you have 500, 1 plus 0.065 over 365 raised to the 3650. And so we get 957 and 71 cents. I notice that that's even less. The more you compound, it turns out that you are making more money the more you compound, but you're getting less and less of it every time. So that's plus 162. Anyway, on the homework, you're going to see problems that are just set up like this, and all they want you to do is plug in the numbers and crank it out. And whatever you get as your answer, that's your answer. Just be sure to go to 2 decimal places. The thing that people get confused about is the ends. So I wanted to elaborate on where you plug in the ends into the formula. All right, almost done. Last 2 pages. So there is another formula called compounded continuously. And the nerd in me just doesn't want to give you the formula. I want to show you how it's created. So what they do is you have this formula, but it turns out that r over n is the same thing as 1 over n over r. And just to show you, I'm going to multiply by r on the top and the bottom. Well, let me prove it to you. I'm going to start out with this guy. I'm going to multiply by r on the top and bottom. The r's cancel, and you're left with r over n. So these 2 things are the same. And I'm going to use that for this next equation. So in this next equation, I'm going to put 1 over n over r, and I'm going to put r over r right here. Perfectly legal. Anything over itself is 1. Multiplying by 1 doesn't change the equation. And I just showed you that r over n is the same thing as this. All right. Now, I still have 1 over n over r here. And up here in the exponent, I'm going to get these 2 and put them together. So notice that now I have the same variable, n over r, n over r. I changed the name. Instead of saying n over r, let me call it m. And we're compounding it continuously. So if you compound continuously, that means you're compounding more than just per day, more than just every second. You're compounding all the time. So you're basically n is going toward infinity. But since m is n over r, notice n is in the numerator. If the numerator goes to infinity, then so does m. So I have this guy, which is the same as this guy. And we just talked about this. This guy here is Euler's number. And so all of that is E. So all of that ugly stuff just turns to an E, and there you go. You have your formula for compounding continuously. Okay, so if the formula is anything else, So this is for compounded annually, monthly, quarterly, daily, etc. So anytime that you can actually count how many times per year it's compounded, you use this formula. Whenever it's compounded continuously, though, we're going to use this formula. They're two separate formulas. All right, and notice in this one that there's no n in the compounded continuously formula. It's just p e to the rt. Now, this proof is just me being nerdy. I wanted to show you how the equation gets up. They don't force you to memorize the proof in our class, but they do want you to know the two formulas. So compounded continuously, p e to the rt. If it's any other type of compounded, it's the formula that we were using on the last page. So let's do a problem with Pusheen. So Al needs to borrow $15,000 to buy a car. He can borrow the money at 6.4% interest compounded continuously for 5 years. How much interest would Al end up paying? All right. So Al wants to borrow a car. He needs this much money. He can borrow money at 6.4% interest. That's going to be my R. Compounded continuously. This tells us the formula to use. That's the formula we're going to be using for 5 years. So this tells me that T is equal to 5. How much interest would he end up paying? All right, so we're going to plug everything in. I know my formula is A equals P e to the RT. So he needs $15,000. That's how much he's borrowing from a bank. E, the rate is 0.064, and T is 5. And that's all you got to do. Notice they gave me all the information. They said, here's R, here's T, oh, there's P, and you just plug and chug. So I go to my calculator, 15,000 e to the 0.064 times 5. So A is equal to 20,656 and 92 cents. Okay, we're not done yet though, because notice the question said, how much interest would Al end up paying? So interest-wise, all we're going to do is, this is how much he ends up paying. And interest is a basic formula. Interest is just total paid minus total borrowed. So he pays 20,656.92, but notice he borrowed 15,000. And so if you subtract the two, you'll get 5,656 and 92 cents. So that's how much he pays in interest. And for a car, that sounds about right. Usually if you buy a car new, you're going to be paying about that much in interest if you're paying on time or if you end up paying a little early. Right. So anyway, these are the word problems you're going to see in this section. They're very straightforward, and they're what I call plug and chug. You already have the formulas. Sometimes it's A equals P e to the RT if it's continuous. If it's not continuous, it's going to be this formula instead. And all you do is read the word problem and plug in the values that they give you. So let's finish this off with this last word problem, and then we're done. The atmospheric pressure on an object decreases, blah, blah, blah. If A is the height, blah, 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 then the pressure. And so they give me the equation. So there's a lot of fluff in this equation, but in this word problem. But all we need to care about is that formula. And they say find the atmospheric pressure at sea level. So notice A is the height above sea level. So my formula, sea level, if we're at sea level, that means that A is equal to 0. Sea level, A is the height above sea level. So here they're just saying plug in 0. And when you plug that in, you just get 760. The units are mmHg. So that's it. Determine the atmospheric pressure at the top of Mount Everest, which is 8,848 kilometers above sea level. And so notice 8.848 kilometers. A is the height in kilometers above sea level, so I'm literally giving you the value for A. And all they want you to do is plug it in. So this is a really happy problem. Plug and chug. So it's 760 e to the negative 0.13, 8.848. So if they give you a non-money related problem, they're going to give you the formula. And all you got to do in this section is plug it in. We haven't gotten to where you're solving them yet. Okay, so make sure I typed it in right. So 240, round to the nearest whole unit. So 240.559. So rounding to the nearest unit, that would be about 241 mmHg. So these word problems are meant to be, they try to scare you with all the scienciness of it. But all it is here's an equation, plug in 0, plug in 8.848. That's all they want you to do. All right, so I know this section was kind of all over the place. We started with the graphs, and then we shifted from the graphs to these word problems. But if you have any questions, please let me know. Yeah, y'all have a good day.